Okay, so welcome back. This has been a project that's been going on for many years. So it's now complete and finally it's good enough to show you guys. This is a linear amplifier built on two Golf Uniform 81 tubes. I was inspired by Echo X-Ray 8 Alpha, Sergei Paskov. And this is my take on his construction. It's nothing like his, but I have incorporated some ideas of my own. I've stolen a lot of ideas from other people, and this is what I came up with. So stay tuned. Okay, so on top here we have the RF deck. It is fully motorized. We can see here a C1. It's got its own stepper motor and position feedback. That's a 10-turn Hall sensor. A potentiometer would have been just fine, but I chose to go with Hall sensors. In the middle here we have L1, which is a variable coil which sits in series with this fixed coil. It's a bit hard to see. And way out there is C2 and its motor. This little gadget, that is my take on Sergei Paskov's plate capacitance neutralizing coil. This is it forms a parallel resonant circuit with the frequency in use, effectively cancels out some of the plate capacitance and increases efficiency on the higher bands. Padding capacitors for C1 are 80 and 160 meters. Padding capacitors on the other side there for 80 and 160 as well. And here are the tubes. Golf Uniform 81. And you can see here that I had to add these wide copper strips to the suppressor grid because I was having instability issues, but these straps solved everything. So what else? Yeah, you can see there's no plate choke on this amplifier. Oh, sorry, I am floating the entire tank circuit at RF and high voltage. So all of the components here, they see 3000 volts under load plus the RF, and the feed, it's hard to see from this side, but it comes in at the 50 ohm side. And the reason for doing that was well, I wanted to try it because I read about it, and I wanted to I wanted just to try it and see if it's possible, and it is. And since I feed the high voltage at the 50 ohm side, there is no chance of the plate choke failing. Okay, so that's the RF deck on top. Down here we have the logic chassis, as I call it. Here we have the power electronics. We have the screen grid rectifier. What else? We have the bias supply, main contactors. We have the front panel controls. We have the main fuses. We have the 12-volt rectifier and stabilizer. And sorry, I'm just gonna go in the back here. Turn this a bit. So as you can see here in the back, there's your bias supply down here. This is the interconnect between the logic chassis and the power supply in the bottom. We'll get to that soon. Here we can see the small coax that comes from the directional couplers that sit inside of the RF deck. Inside this logic chassis I have an Arduino Mega. The Arduino Mega runs the stepper motors. It keeps the memory of preset frequencies, and it is well, it's controlling the amplifier basically. It measures all the currents, voltages throughout the amplifier, and it is I have a protection circuits. This is the trip relay, so whenever the Arduino senses an overcurrent, it drops this relay, which in turn drops the main contactors, which removes primary voltage from the high voltage transformer. And that works, and it's completely custom configurable over serial, so I'm quite pleased with that. Down in the bottom we have the heavy stuff. So I'm just gonna come over here. Hopefully you can see. Here we have the high voltage transformer, full wave rectifier, and a UI core transformer. This one is rated at 3 kVA, which means a continuous 3 kilowatt draw on this one. And since we in Sweden we have 3-phase power in every household, I am running this transformer, the transformer primary. I'm using 2 phases, which means that I'm putting 400 volts across the primary, so there's no blink in the lights. This little circuit board, this is the high voltage metering and dropout board. It senses about over 2000 volts. It sends an OK signal and pulls in. See, there's a little relay on there, and that relay activates at 2000 volts, which in turn activates the contactors for the screen grid transformers. Bleeder resistors, sorry, kind of hard to film down here, it's a bit dark. Heavy duty stuff, and let's see if we can get in here. Sorry, it's a mess. Soft start contactor, and the smaller contactor is the screen grid contactor. And we can also see that there's a variac in here, and that variac feeds the primaries of the screen grid transformers. So I got sick and tired of trying to make a screen grid rectifier that would not blow up. So I ended up just using a variac and just go with that. The voltage drop on the screen is about 50 volts, which I think is well, it'll do for now. You can see that I was inspired a bit by the Collins, the old Collins 30K series. This is a mesh net here, brass mesh. I was gonna put a glass window there, but you know, I cut it too small and I ended up just using the brass, and that turned out great. Metering, we have plate volts, plate current, screen current, and screen volts, and this is also configurable to show control grid current. The controls on the amplifier is very few, and this is your main on and off switch. This is the high voltage on, and this is the high voltage off. So these two holes, I'm gonna fill them, but they were from a failed attempt of a regulated screen grid power supply. So everything is made by me. The cabinet, angle iron welded together, all the panels, the louvers, I've cut these and I just use a rough forming tool to punch these louvers, and they turned out decent, I must say. The metering, it's these meters are driven by an Arduino, by the same Arduino Mega as does all the other things. It drives these meters using a digital to analog converter. So a DAC to drive these, and it's working quite well. Just gonna turn on the high voltage, and there you could hear the step start. So the step start is a timer relay and a 33 ohm 100 watt resistor in the primary. So the step start timer is set to about, you know, just a couple of seconds. Anyway, we can see here that we're running at about 3,500 volts idling. We're idling at about 20 milliamps of screen current, which is due to the fact that I have leader resistors which draw basically to 26 milliamps, so that's quite good. And the screen volts is a bit high. It's not a kilowatt. The meter is not scaled properly, so it's idling at about 900 volts right now, and that drops to about 850 volts under load. So the resting current is a tad high at 400 milliamps. That's due to the biasing being a little low, but that's an adjustment I'm gonna do later on. So let's go on air and see what it does, and I'm also going to show you the user interface. Okay, so this is how the user interface looks like, and I should probably do a screen recording, but I just wanted to show you guys this, so just bear with me. So what this does, or well, say like this, the amplifier can be controlled from any serial monitor. It uses RS485 to communicate between the amplifier and an Arduino Nano. The Arduino Nano also has an RS485 transceiver. And the reason I did that was because I'm planning to use this remotely, and I didn't want to run serial for like 70 or 80 meters, so I'm gonna use RS485, so I can place this, you know, anywhere I like it on the property later on. So I can send all of the commands that I'm using to control this amplifier over serial, or over a let's call it a modified Modbus, a simplified Modbus protocol. So I can individually tune all of the stepper motors or capacitors. I can tune this amplifier like I would with a normal, with this one. I can do the same using C1, L1 and C2 up and down, and I can also send commands like C1++, and that will move C1 100 steps forward, C1 minus minus, 100 steps backwards, so on. And when I'm tuned to a good power output versus efficiency, I hit save, and what happens then is that the frequency that you're on, that gets saved into EEPROM together with these settings. And I do this for at least 2 points in the band, so the lowest point and the highest point. And what happens then if we're, so as you can see, this one's following the VFO on my radio. So what happens is, if we want to tune this at 726 on 40 meters, I just hit tune, and the amplifier interpolates between those 2 points, and that seems to be quite right. You know, I'm surprised that it's working so well. What else can I say about this? Well, as you can see, I'm using Win4K3 Suite, which pulls the K3 for the frequency, and it shares a virtual COM port with my user interface. We can see that I can choose what COM port the rig is listening to, and the Arduino, well, let's call this the interface between the computer and the amplifier. What else do we have here? Well, we can see we can set this, show power bars on and off. We can, well, show efficiency. That's not active. I'm gonna remove that. I forgot about it. I can set the power meter to show average or PEP, and the motor control I can set it between stepping and jogging. So jogging is good for, it's more of a continuous movement than the steps. Here we can set the protection and trip thresholds. So currently the plate current is set at 1500 milliamps. There's a small delay there, 10 milliseconds. And the screen is set at 550 milliamps. If the amplifier trips on overcurrent, this is where to reset it. There's also a function that monitors the position feedback potentiometers. So I set it up in code that for the value to be valid, it has to be above a certain point and below a certain point, which means that if you get a short circuit between 5 volts and the potentiometer sense line, it will trigger a fault. The same goes if we short the output of the potentiometer to ground, we will get a fault which inhibits movement. And I've added the possibility to send a command over serial to list the 20 last valid values. And that is because if a potentiometer fails, I can just put a new one in and adjust that to the latest known good value. That way I don't lose track of the variable capacitors. So hopefully that makes sense. So now we're gonna go on 17 meters. You can see here the rig is on 1718073. We hit tune. And the tuning cycle, the first cycle, it runs all the 3 motors, and each one of the motors, they stop at their target position until there's only one left. And when they are in like their course mode, we get into the final push. So that's why it's a bit slow. I can probably speed this up a little bit. And the final tuning step is that the controller, it looks for the value and it pushes the stepper motors just a few steps until we are dead on target. So now let's see, 18073. Let's see what we do. So I'm driving this with 65 watts, and that is the full output. Above 65 watts, we start to draw a little bit of control grid current. So if you can see that, it's gonna move closer. Sorry. So there you have it. It's a nice amplifier. It took me 4 or 5 years to build this, but it's working good. And since I got the software to play along, it's very fun to use. So leave a comment, and if you want to know something specific, leave a comment, and I'll try to shoot a video of that, and to make a more in-depth explanation. So until then, thank you. Somethin from Sweden. Bye bye.